Have you ever stopped to think about what really exists in the depths of the ocean? Beneath the dark cover of the waters, there is an unknown world, full of mysterious phenomena that science is only beginning to unravel. What if the depths held secrets that could help us better understand our own planet? In this video, we will explore the most inhospitable and fascinating regions of the ocean, revealing impressive natural phenomena and creatures that look like something out of a fictional film. Prepare yourself for a unique journey that will enrich your knowledge and take you to places few have dared to go. Stay until the end and discover what we know, and what remains to be discovered, about the bottom of the sea. The vastness of the ocean is overwhelming. Covering over 70% of our planet's surface, the ocean holds almost 97% of Earth's water. Yet, despite its immense size and presence, more than 80% of the ocean remains unexplored. To put it in perspective, we know more about the surface of Mars than we do about the depths of our own planet. This staggering fact fuels both scientific curiosity and a sense of adventure, as researchers continue to uncover secrets hidden in these remote, enigmatic places. The deep ocean is divided into different zones, each defined by the level of sunlight that can penetrate. Past a certain depth, sunlight completely fades, and a dark, cold world takes over. The twilight zone, or mesopelagic layer, lies between 200 and 1,000 meters and is the last region where faint, filtered light still reaches. Below this lies the midnight zone, or bathypelagic layer, where complete darkness reigns. Temperatures drop close to freezing, and pressures can reach over 100 times what we experience at sea level. But even further below, at depths of 6,000 meters or more, lies the Hadal zone, named after Hades, the god of the underworld, a place of near-complete isolation and unfathomable pressure. It's here that life encounters its greatest challenges, surviving against seemingly impossible odds. What fascinates scientists and explorers alike is the resilience of life in these depths. Creatures inhabiting these zones must endure conditions that would be fatal to most known organisms. But these harsh environments give rise to strange adaptations, creating beings that appear more alien than earthly. As researchers push deeper, using advanced submarines and robotics, they encounter organisms with bioluminescent properties, bodies designed to withstand crushing pressure, and behaviors entirely foreign to our usual understanding of life. Yet, the mysteries of the deep ocean go beyond its biology. There are unexplained phenomena, such as underwater lakes or brine pools, dense pockets of saltwater that sit like pools within the ocean itself, creating alien landscapes complete with their own ecosystems. Scientists have also discovered hydrothermal vents, where superheated, mineral-rich water bursts from cracks in the ocean floor, supporting unique organisms that thrive in the mineral-rich waters. These vents create an ecosystem entirely independent of sunlight, challenging long-held assumptions that life on Earth must rely on solar energy. The allure of these unexplored depths is not just in the strange creatures and landscapes, it's in the opportunity to discover life forms, ecosystems, and geological phenomena unlike anything seen on land. Every dive, every sample collected from these regions opens new windows into an otherwise hidden part of our world. The more we uncover, the more we realize just how little we know. These discoveries continually reshape our understanding of biology, chemistry, and geology, driving humanity's endless curiosity to explore what lies in the darkest corners of our planet. As we continue, we'll delve into some of the most remarkable phenomena of these deep, dark waters, places where scientific discovery meets the thrill of the unknown. The abyssal zones of the ocean present some of the most extraordinary natural phenomena on Earth. From superheated underwater vents to immense underwater lakes, these areas defy conventional science, hosting conditions and life forms that challenge our understanding of biology and geology alike. As we descend deeper into these dark, alien landscapes, let's explore some of the most fascinating phenomena found in these extreme ocean zones. One of the most studied and awe-inspiring features in the abyssal depths is the hydrothermal vent. Located along tectonic plate boundaries, these vents are formed when seawater seeps down into cracks in the ocean floor, heats up to extreme temperatures due to contact with magma, and then is expelled back into the sea through chimney-like structures. These jets of superheated water, often reaching temperatures of up to 400 degrees Celsius, contain an abundance of minerals like sulfur, copper, and zinc, which nourish a unique set of life forms. Unlike most ecosystems on Earth, which rely on sunlight, the organisms around hydrothermal vents thrive through a process called chemosynthesis, where bacteria convert the vent's mineral-rich compounds into energy, supporting an entire food web. These vent ecosystems are home to some of the ocean's most bizarre creatures. Giant tube worms, clams, and shrimp cluster around these vents, relying on symbiotic bacteria to sustain them. The tube worms, for example, lack mouths and digestive systems. Instead, they house bacteria within their bodies that convert chemicals from the vents into nutrients. This incredible adaptation allows life to flourish in conditions once thought to be incompatible with survival, reshaping our understanding of the requirements for life. For scientists, these ecosystems hint at the possibility of similar forms of life existing in extreme environments on other planets or moons, such as Jupiter's moon Europa. Another captivating feature found in the abyssal plains is the underwater lake. These are high salinity brine pools, where the water is so dense with salt that it settles at the ocean floor, creating a distinct layer that doesn't mix with the surrounding seawater. These brine pools, often referred to as lakes within the sea, are toxic to most marine life. Yet, some species have adapted to survive at the edges of these brine pools, finding unique ways to tolerate the high salt concentrations. The discovery of brine pools adds another layer of mystery to the deep ocean, as these pockets of ultra-salty water create otherworldly landscapes complete with their own mini ecosystems, where the rules of survival are unlike any seen elsewhere on Earth. Then there is the phenomenon of bioluminescence, a natural wonder prevalent throughout the deep ocean. Bioluminescence occurs when certain organisms produce light through chemical reactions within their bodies, often to communicate, lure prey, or deter predators. In the deep sea, where sunlight does not reach, bioluminescence becomes a crucial survival tool. Fish, jellyfish, and even some types of bacteria and algae have evolved to emit light, creating a surreal display of glowing forms moving through the darkness. One of the best-known bioluminescent creatures is the anglerfish, which uses a glowing lure on its head to attract prey. But bioluminescence is not limited to large predators. Smaller organisms, like plankton, also emit light, creating sparkling displays across the ocean's dark expanse. Beyond the individual organisms, the deep sea itself undergoes unique geological transformations. The ocean floor is constantly shifting, with tectonic activity resulting in underwater mountains, canyons, and even volcanic eruptions. The Mariana Trench, the deepest known point on Earth, was formed by the convergence of tectonic plates, creating a canyon that plunges nearly 11 kilometers below sea level. In areas like these, the pressure is so intense that it compresses water molecules, making the water denser than at the surface. These geological formations are a reminder of the powerful forces at play in shaping our planet, forces that remain hidden from view yet have a profound impact on the ocean's environment. One particularly mysterious phenomenon found in these depths is the deep scattering layer, sometimes referred to as the ocean's false bottom. This layer consists of a dense aggregation of fish, squid, and other organisms that migrate vertically each day, creating a phenomenon that confounded early sonar technology. During the day, this layer stays deep in the ocean, but at night, it rises closer to the surface. This daily migration, the largest on the planet in terms of biomass, is a survival tactic. By staying deep during daylight hours, these creatures avoid predators, only coming up to feed under the cover of darkness. The deep scattering layer plays a crucial role in ocean ecosystems, helping to regulate nutrient cycles and serving as a significant link in the oceanic food chain. Finally, it's important to consider the role of cold seeps in the deep ocean. Cold seeps are areas where hydrocarbon-rich fluids, like methane or hydrogen sulfide, slowly seep from the seabed. These regions, often rich in minerals, support unique ecosystems similar to those around hydrothermal vents, but on a slower, more stable scale. Cold seeps are a significant area of interest because they contribute to the formation of methane hydrates, ice-like structures that trap large amounts of methane. If released in large quantities, this trapped methane could impact the global climate. Therefore, studying cold seeps helps scientists understand both the ecological dynamics of the deep sea and the potential implications for climate change. These phenomena are more than just isolated wonders. They reveal a hidden world where life has adapted in astonishing ways to some of the harshest conditions imaginable. Each discovery challenges preconceived ideas and opens up new questions. What other mysteries await in the depths of our oceans? As we push forward, we're continually reminded of how little we know and of the profound impact that these abyssal phenomena have on our planet's health and stability. Beneath the waves, in the cold, crushing darkness of the ocean's depths, some of the planet's most astonishing life forms have evolved. These creatures live in conditions that would be lethal to most organisms, and their adaptations for survival are as fascinating as they are peculiar. The deep sea is like an alien world, where animals have evolved in isolation from the sun, relying on unique strategies to endure extreme pressure, frigid temperatures, and perpetual darkness. One of the most iconic deep-sea creatures is the anglerfish, easily recognizable by the bioluminescent lure that dangles from its head. This fishing rod acts as a trap for unsuspecting prey, drawing them close enough for the anglerfish to snap them up. Its bizarre appearance is matched by its behavior. In many anglerfish species, the much smaller male fuses with the female upon mating, becoming part of her body and dependent on her for nutrients. This extraordinary adaptation highlights the extreme lengths to which deep-sea organisms go to survive and reproduce in an environment where encounters with mates are scarce. Another fascinating resident of the abyss is the gulper eel. Unlike most eels, the gulper has an enormous, hinged mouth that allows it to swallow prey much larger than itself. This adaptation is essential in the nutrient-scarce depths, where food is scarce and irregular. When it encounters a potential meal, the gulper eel's massive mouth can expand to capture it in one swift movement. Its body, however, is relatively thin and streamlined, designed for conserving energy and maneuvering with minimal effort. Bioluminescence is a common trait in many deep-sea creatures. The vampire squid, for example, uses bioluminescent displays to startle predators and mask its escape. With large eyes adapted to capture even the faintest traces of light, the vampire squid appears almost otherworldly, gliding through the water with webbed arms that it can retract or spread like a cloak. This behavior, combined with its light-producing abilities, enables the vampire squid to survive in some of the deepest, darkest regions of the ocean. Meanwhile, the deep-sea octopus known as the Dumbo octopus has developed a strategy of slow, energy-efficient movement. Named for its ear-like fins that resemble Disney's character Dumbo, this octopus glides gracefully through the water, using minimal energy to conserve resources in an environment where food is scarce. The Dumbo octopus also lays its eggs on the ocean floor, protecting them in sheltered crevices where they are less likely to be disturbed by predators. One of the most unexpected adaptations among deep-sea creatures is gigantism. In these depths, certain species grow to sizes far larger than their shallow-water relatives, a phenomenon known as deep-sea gigantism. The giant isopod, a relative of the common pill bug, can reach lengths of over 30 centimeters. This adaptation may help the isopod store more nutrients in a habitat where meals are few and far between. The colossal squid is another example, with eyes as large as dinner plates, allowing it to detect even the faintest movements of prey in the dark. Scientists are especially interested in the role of bioluminescence in the deep sea. For creatures like the dragonfish, bioluminescence is both a lure and a weapon. The dragonfish has light-producing organs along its body, which it can flash to communicate, attract prey, or startle predators. It also has a bioluminescent headlamp under its eyes, allowing it to see without giving itself away to predators or prey. This ability to produce light from within, adapting it for various purposes, is one of the ocean's most astonishing biological phenomena and is still a major focus of scientific research. Beyond bioluminescence, some creatures have evolved to handle extreme pressures in unique ways. The snailfish, discovered in the Mariana Trench, has a gelatinous, almost translucent body that lacks the hard bones typical of fish in shallower waters. This lack of rigid structure allows it to survive the immense pressure of the hadal zone, which would crush other animals. Scientists studying the snailfish hope to understand more about the biochemical adaptations that allow these creatures to thrive in such conditions, shedding light on the possibilities of life in extreme environments elsewhere in the universe. The adaptability of deep-sea life extends even to feeding habits. The scavenger lifestyle is common, with creatures like the deep-sea hagfish taking advantage of any organic material that drifts down from the surface. Hagfish have slimy, eel-like bodies and produce copious amounts of mucus when threatened. This slime acts as a defense mechanism, clogging the gills of potential predators and allowing the hagfish to escape unharmed. In addition to scavenging, hagfish have the unique ability to tie their bodies into knots to gain leverage when feeding, a remarkable behavior that allows them to consume food efficiently in an environment where every meal is precious. The creatures of the deep sea reflect the adaptability and diversity of life on Earth. From bioluminescent displays to unusual reproductive methods, their strategies for survival are as diverse as they are innovative. Each of these animals has evolved specifically to thrive in the challenging environment of the ocean's depths, turning what seems like an inhospitable wasteland into a thriving ecosystem. As we learn more about these remarkable creatures, we gain insight not only into the resilience of life on Earth but also into the potential for life in other extreme environments throughout the cosmos. Exploring the deep ocean is one of the most challenging and rewarding endeavors in modern science. Unlike space exploration, where advanced telescopes and spacecraft can observe distant objects, exploring the deep ocean requires physically descending into a realm of extreme pressure, darkness, and isolation. In recent decades, technological advancements have allowed scientists to probe deeper than ever before, revealing breathtaking insights into a world previously hidden from human view. However, each new discovery is hard-earned, the result of intricate engineering, careful planning, and the courage to venture into some of the most inhospitable places on Earth. One of the earliest breakthroughs in deep-sea exploration was the development of submersibles, self-contained underwater vehicles capable of descending thousands of meters below the ocean's surface. In 1960, the bathyscaphe Trieste made history by descending to the bottom of the Mariana Trench, reaching a depth of nearly 11,000 meters. The Trieste, a spherical pressure chamber attached to large gasoline-filled floats for buoyancy, carried two men, Jacques Picard and Don Walsh, to the ocean's greatest depth. This milestone was monumental, but the journey was brief, and the technology of the time allowed only limited observation. However, the Trieste's success proved that human exploration of the deep ocean was possible, setting the stage for future advances. Today's submersibles, such as Alvin and the more recent Deep-Sea Challenger, offer significantly enhanced capabilities. These modern vehicles are designed with reinforced titanium or composite materials to withstand immense pressures, and they are equipped with advanced lighting, cameras, and robotic arms that allow for precise scientific work. Equipped with high-resolution cameras, these submersibles can capture detailed images and video, providing researchers with the ability to observe and document deep-sea ecosystems in unprecedented detail. The Deep-Sea Challenger, piloted by filmmaker James Cameron, made a solo descent into the Mariana Trench in 2012, capturing extensive footage of this remote environment and inspiring a renewed interest in deep-sea exploration. While manned missions offer valuable insight, they are limited by the risks and costs associated with sending humans into extreme depths. To overcome these limitations, scientists increasingly rely on remotely operated vehicles, ROVs, and autonomous underwater vehicles, AUVs. ROVs, such as Jason and Nereus, are tethered to research vessels on the ocean's surface, allowing scientists to control them in real time from a safe distance. With sophisticated sensors, manipulator arms, and sampling equipment, ROVs can gather samples, measure environmental conditions, and document findings without risking human lives. AUVs, on the other hand, operate independently, navigating pre-programmed routes to map the seafloor, take measurements, and even collect samples autonomously. The versatility and safety of ROVs and AUVs make them indispensable tools in the exploration of the deep ocean. Advancements in sonar technology have also revolutionized our understanding of the ocean floor. Using multi-beam and side-scan sonar, scientists can map vast stretches of the seabed in remarkable detail. These sonar systems send out sound waves that bounce back upon hitting the seafloor, allowing researchers to create high-resolution maps of underwater mountains, trenches, and canyons. The discovery of hydrothermal vent fields, for example, was made possible in part through sonar mapping, which helped scientists locate potential areas of tectonic activity on the ocean floor. Such maps provide critical information, guiding submersibles and ROVs to areas of interest where more detailed exploration can take place. One of the most exciting developments in deep-sea exploration is the use of deep-sea observatories. These fixed stations, installed on the ocean floor, are equipped with sensors that continuously monitor environmental conditions, such as temperature, pressure, and chemical composition. Observatories like the Ocean Networks Canada's Neptune and the European Multidisciplinary Seafloor and Water Column Observatory, EMSO, provide real-time data on the deep ocean, enabling scientists to study changes over time. This continuous monitoring is essential for understanding the dynamics of deep-sea ecosystems, as well as detecting phenomena such as earthquakes, volcanic eruptions, and methane seepage from the seafloor. By establishing a network of observatories, researchers can gain a more comprehensive understanding of the deep ocean and its interactions with the global climate system. Another frontier in deep-sea exploration is the development of molecular and genetic tools. Recent advances in DNA sequencing have allowed scientists to identify and study the genetic makeup of deep-sea organisms, many of which have unique adaptations to high-pressure, low-oxygen environments. Through techniques such as environmental DNA, EDNA, sampling, scientists can detect the presence of species based on genetic material they leave behind in the water, providing a non-invasive way to study biodiversity in hard-to-reach areas. This molecular approach is transforming our understanding of deep-sea ecosystems, revealing not only new species but also the genetic pathways that enable life in extreme conditions. Such insights may one day lead to breakthroughs in medicine, biotechnology, and our understanding of the potential for life in similar environments on other planets. Finally, artificial intelligence, AI, and machine learning are beginning to play a significant role in analyzing the vast amounts of data collected from the deep sea. As more submersibles, AUVs, and observatories gather data, researchers are faced with the daunting task of processing and interpreting these massive datasets. AI algorithms can sort through images, videos, and environmental data to identify patterns, classify organisms, and even predict ecological trends. For instance, AI systems can be trained to recognize and catalog species in footage captured by ROVs, significantly speeding up the research process. As these technologies continue to develop, they will enable more efficient and effective exploration, helping scientists to unlock the deep ocean's secrets at an unprecedented pace. Exploring the deep ocean is a testament to human ingenuity and perseverance. Every technological breakthrough brings us closer to understanding a realm that has remained hidden for millennia. Through submersibles, ROVs, sonar, genetic research, and AI, we are slowly peeling back the layers of mystery that shroud the ocean's depths. Yet, despite all our advancements, the deep sea remains one of the final frontiers on Earth, a place that challenges our perceptions and reminds us of the vast unknown. As technology advances, we are on the cusp of discovering more than ever before, uncovering insights that could reshape our understanding of life on Earth and beyond. While the deep ocean is a remote and largely uncharted world, it is not immune to the influence of human activity. Despite its isolation, pollution, resource extraction, and climate change are altering deep-sea ecosystems in ways that scientists are only beginning to understand. Human activity on land and in shallow waters has cascading effects that reach even the darkest corners of the ocean, threatening fragile ecosystems and potentially disrupting the delicate balance of life at extreme depths. In this chapter, we explore how the byproducts of modern industry and consumption are impacting the depths of the sea, and what steps are being taken to protect these vital ecosystems. One of the most pervasive threats to the deep ocean is plastic pollution. Although plastics are mostly introduced to the ocean at the surface, currents, degradation, and sinking debris carry microplastics and larger fragments down to the seafloor. Deep-sea exploration has revealed that plastic waste, from single-use bags to fishing nets, is accumulating even in the most remote trenches. In the Mariana Trench, for example, researchers have documented plastic bags and other debris at depths of nearly 11,000 meters. This plastic not only contaminates the habitat but also poses a physical hazard to deep-sea creatures, which may ingest or become entangled in the debris. Studies have shown that microplastics are already present in deep-sea organisms, raising concerns about the health impacts of these pollutants on oceanic ecosystems and the potential for toxins to enter the food chain. Beyond pollution, deep-sea mining is emerging as a significant threat to the ocean's depths. Companies are increasingly interested in extracting minerals such as cobalt, nickel, and rare earth elements from the seabed, which are in high demand for electronic devices and renewable energy technologies. The deep sea is home to mineral-rich deposits, including polymetallic nodules and massive sulfide deposits near hydrothermal vents. While these resources are valuable, the extraction process is highly disruptive. Mining operations could destroy fragile ecosystems, particularly near hydrothermal vents, where unique communities of organisms rely on chemical energy rather than sunlight. These ecosystems are often slow-growing, and the damage caused by mining could take centuries to heal, if it is reversible at all. The potential consequences have led to calls for a moratorium on deep-sea mining until its environmental impact is fully understood. Climate change is another profound driver of change in the deep ocean. Rising global temperatures are causing shifts in ocean circulation patterns, leading to changes in the distribution of nutrients and oxygen levels. These alterations can have far-reaching effects on deep-sea ecosystems, which are finely tuned to specific conditions. Oxygen minimum zones, where oxygen levels are already low, are expanding as a result of climate change, creating dead zones, where few organisms can survive. Additionally, ocean acidification, driven by increased carbon dioxide absorption, affects the stability of calcium carbonate structures, which many deep-sea organisms rely on to form shells and skeletons. Coral reefs in the deep sea, for instance, are particularly vulnerable to acidification, which weakens their structures and limits their growth, threatening the species that depend on these habitats. Fishing practices, too, have a lasting impact on the deep ocean. Deep-sea trawling, in which heavy nets are dragged across the seafloor, is highly destructive. This method is used to capture species that live at great depths, such as orange roughy and Patagonian toothfish, but it also destroys vast areas of seafloor habitat. Deep-sea corals, sponges, and other slow-growing organisms are easily damaged by trawling, and once destroyed, these habitats can take centuries to recover. In addition to damaging the environment, deep-sea fishing poses a sustainability problem, as many of the targeted species are slow to reproduce and vulnerable to overfishing. Efforts to regulate and reduce deep-sea fishing are ongoing, with some regions implementing protected areas to allow ecosystems to recover. Despite these challenges, there is a growing movement to protect the deep sea. International organizations, including the International Seabed Authority, ISA, and various environmental groups, are advocating for stricter regulations to limit the environmental impact of human activities. Marine Protected Areas, MPAs, are one of the primary tools used to safeguard vulnerable regions of the ocean, and there is increasing interest in establishing MPAs in deep-sea areas. Additionally, scientists are developing more sustainable technologies and practices for resource extraction and waste management, aiming to minimize damage to these ecosystems. Public awareness and advocacy are also crucial, as greater understanding of the deep sea's importance can lead to more support for protective measures. The impact of human activities on the deep ocean serves as a powerful reminder of the interconnectedness of Earth's ecosystems. Although the deep sea might seem remote, it plays a critical role in regulating global processes, from carbon storage to nutrient cycling. Preserving the health of deep-sea ecosystems is essential not only for the survival of the remarkable species that inhabit them but also for the stability of the planet as a whole. By recognizing the effects of our actions and working towards more sustainable practices, we can help ensure that the deep ocean remains a vibrant and thriving part of our natural world. As our understanding of the deep ocean grows, so does our recognition of its vast potential and importance for humanity's future. The ocean's depths hold untapped resources, offer clues to the origins of life, and may even harbor insights into new technologies and medicines. However, the future of deep-sea exploration is not without challenges, as the need for sustainable practices and international cooperation becomes ever more critical. In this final chapter, we explore the exciting possibilities that lie ahead for deep-sea exploration and consider the broader implications for science, industry, and environmental conservation. One of the most promising areas for future exploration is the discovery of novel species and ecosystems in the deep ocean. Each mission to the ocean's depths reveals new and unique organisms, many of which are unlike anything found elsewhere on Earth. These discoveries could expand our understanding of biology, genetics, and evolution, offering new insights into the resilience and adaptability of life. Some scientists even believe that studying these organisms could provide clues about how life might exist on other planets, particularly in extreme environments like the ice-covered oceans of Jupiter's moon Europa. By pushing the boundaries of biological science, deep-sea exploration may help answer fundamental questions about life's origins and possibilities beyond our planet. The deep sea is also seen as a potential frontier for medical and pharmaceutical research. Many deep-sea organisms produce unique biochemical compounds to survive in harsh conditions, such as high pressure and low oxygen. These compounds have attracted the interest of researchers, who hope to harness them for new medical treatments. Some deep-sea bacteria, for instance, produce enzymes that are stable at extreme temperatures and pressures, which could have applications in drug development and biotechnology. Similarly, the bioluminescent proteins found in certain deep-sea animals have already contributed to advancements in medical imaging and research. By studying the adaptations of deep-sea species, scientists could unlock new tools for combating diseases and improving human health. Another potential benefit of deep-sea exploration lies in the discovery of valuable resources. As demand for minerals and metals increases, the deep sea is being considered as a source of rare elements needed for electronics, renewable energy technologies, and other industries. Polymetallic nodules, which contain copper, cobalt, manganese, and nickel, are abundant on the ocean floor and have sparked interest from mining companies. However, the extraction of these resources must be carefully managed to avoid irreversible damage to fragile ecosystems. The future of deep-sea mining will depend on developing sustainable practices that balance the need for resources with the preservation of biodiversity and environmental health. Ensuring that resource extraction is conducted responsibly will require close collaboration between scientists, governments, and industry stakeholders. Climate change research is another area where deep-sea exploration plays a vital role. The deep ocean is a significant carbon sink, absorbing vast amounts of CO2 and helping regulate the Earth's climate. Understanding how the deep sea contributes to global carbon cycles is essential for predicting and mitigating the effects of climate change. Researchers are studying processes like carbon sequestration in the deep ocean, where carbon is stored in the form of sediments and dissolved CO2. This knowledge could lead to new strategies for managing atmospheric carbon levels and combating climate change. Furthermore, monitoring changes in deep-sea ecosystems provides early warning signals for broader environmental shifts, allowing scientists to respond proactively to emerging climate challenges. However, the future of deep-sea exploration is not just a matter of scientific curiosity or resource extraction, it is also a question of ethics and international cooperation. The ocean, especially its depths, is a shared resource that transcends national borders. As more countries and private entities become involved in deep-sea research and exploitation, the need for comprehensive regulations becomes increasingly urgent. The United Nations High Seas Treaty, currently under negotiation, aims to create a legal framework for protecting biodiversity in international waters and ensuring that deep-sea activities are conducted responsibly. International agreements like this will be crucial for balancing exploration with conservation, ensuring that the deep ocean's resources are used equitably and sustainably. Advancements in technology will undoubtedly shape the future of deep-sea exploration. Innovations in robotics, artificial intelligence, and underwater communication systems will enable scientists to explore deeper, faster, and more safely. Autonomous underwater vehicles, AUVs, and remotely operated vehicles, ROVs, will continue to be essential tools, allowing researchers to gather data and samples in extreme environments without risking human lives. AI-driven data analysis will enhance our ability to interpret the vast amounts of information collected from the deep sea, revealing patterns and insights that were previously impossible to discern. As technology progresses, our capacity to explore the ocean's depths will expand, potentially transforming our relationship with the marine world. In conclusion, the future of deep-sea exploration holds tremendous promise for humanity. By unlocking the mysteries of the ocean's depths, we have the opportunity to advance science, medicine, and technology in ways that benefit society as a whole. Yet, with this potential comes a responsibility to act as stewards of the ocean, protecting its ecosystems from harm and ensuring that its resources are used wisely. As we look to the future, the deep sea reminds us of both the power and the limits of human endeavor, a realm where exploration meets conservation, and where the unknown continues to inspire and challenge us. The next chapter in the story of deep-sea exploration is just beginning, and its implications may well shape the world for generations to come.